Braving the rain and making it here. Let's see, I feel like I had some questions for you guys. Oh, look at that. So, that time yet is here's the attendance form. Name on there. I had one more thing to say about what we did last time as far as like distance between things, angles between planes. Um, I want to talk about finding the well, actually, so two things I should say. First of all, last time we found the angle between two planes, and I wanted to briefly talk about how we find the line of intersection of those two planes. So real quickly, last time we found the angle between the planes. They were x plus 2y plus 3z equal to 6. And the other plane was x minus 2y plus 4z equal to 8. This was plane 1, and this was plane 2. And we drew a little picture, and parts of the planes looked like this. So like here's your plane 2, and here's your plane 1. Kind of, yeah, okay, sure. And we found the angle between them. I don't recall what it was. Not the point. And the way we found the angle between them was by actually finding the angle between the normal vectors. So we had, this normal vector kind of sticking out this way. There's n1. This normal vector kind of sticking out this way. There's n2. What I want to do now is find the line of intersection. So to find the line of intersection, which is right here, to find this line L, well, just like for any line, in 2 dimensions, we need a point and a slope. In more dimensions, we need a point and a direction. So basically, we need the vector that gives us the direction of this line, and we need a point on this line. The direction vector is probably the easier thing to think about finding, actually. All we're going to do is we're going to take the cross product of n1 and n2. Because if you cross those two vectors, it's going to point in the direction that's perpendicular to both of them, and both those normal vectors are perpendicular to the line that's contained in the plane that the vectors are normal to. So to find the direction, we're just going to calculate n1 crossed with n2. And then that's going to be the usual cross product, ijk. I should say, the determinant of the matrix, ijk, and then n1 normal vector is 1, 2, 3. N2, the normal vector of P2 is 1, negative 2, 4. Which is not too terrible. It's going to be I times, let's see, 2, 3, negative 2, 4. Minus j times 1, 3, 1, 4. Plus k times 1, 2, 1, negative 2. So that's going to give us the vector I times 8 minus 6, which is 14, minus j times 4 minus 3, which is 1, so minus 1j, and then k times negative 2 minus 2, which is minus 4k. Let's double check I did the work right. Looks good to me. That's the easy part to conceptualize. The harder part then is to find a point on the line. Well, this is where we're going to talk about the thing I talked about last class, which is that if you draw a line in space, it's got to go through at least one of the three coordinate planes. Probably two, could be three, but at least one, right? You can't draw a line in space that doesn't go through the floor or this wall or that wall. Not possible. So we're going to assume it goes through one of the planes. Let's say the XY plane. You can make any choice you want. So assume the line L goes through, I can spell, the XY plane. So what that means is z is equal to 0. And then we're going to find the point where these two planes intersect each other when z is equal to 0. Right? Because that point of intersection on that line is also where the planes intersect. Now, here's what's going to happen. If we happen to have made the wrong choice, we pick the plane where the line doesn't actually cross through it, we're not going to get a solution, and then we're just going to do it again, picking a different plane. It's really just a guess a thing, see if it works. It usually works. And if it happens to not work because you happen to get unlucky, pick one of the other two planes. It'll probably go through. It's very unlikely to pick two wrong planes in a row, like almost impossible. So let's see. So we're going to set z equal to 0. And then we're just going to say, well, then we have x plus 2y equal to 6 and x minus 2y equal to 8. We've got very lucky here by design. We're just going to add these together and say 2x plus no y equals 14. So we're going to get x equal to 7. Plugging that back into either of these equations, we're going to get, I think, let's see, if x is 7, y is going to be negative 1/2, I believe, because we have 2y equal to 6 minus 7, which is negative 1. So y is equal to negative 1/2. And then what should happen is that should, well, in fact, nothing else should happen. We did it. We got a solution, right? We can solve the system of equations. Basically, setting z equal to 0 didn't give us like parallel lines here that don't intersect. So our point of intersection is the point 7, comma, negative 1/2, comma, what's the z coordinate? Right, we set z equal to 0. So then the equation of our line, we could write parametrically as x equal to 7 plus 14t, y equal to negative 1/2 minus 1 times t, and z equal to 0 minus 4 times t. And that is the parametric equation of the line of intersection. Yeah. Oh, sure. So I'll remind you what we're doing is right. We're essentially we're doing what's called cofactor expansion, which again you will definitely, well, I say definitely, you should definitely see in 22A. Except a couple quarters ago, someone didn't teach the determinant. I was like, what's going on? Anyway, you should see this in 22A where you take the determinant of any large matrix by picking a row or a column. We almost always pick the first row for cross product because we want the IJK to show up. So you pick the I, then you cross out the row and column that contain that I, and take the determinant of the remaining 2x2 matrix. Same deal for J, except we alternate signs. So it's minus J times the determinant of that 2x2 matrix. And then it's plus K times the determinant of that 2x2 matrix. And then the determinants are just, right, 2 times 4 minus 3 times negative 2. And then 1 times 4 minus 3 times 1. And then 1 times negative 2 minus 2 times 1. Other questions about this example? So one more time. The equations of, yeah, as far as like finding the distance between them. Yeah, like as far as like what the equation of a plane looks like. Yes. But we can talk about it more. Like, so I can say very generically, right? Generically, the equation of a plane looks like kind of like the equation of a line, except an extra variable. So instead of like ax, so in fact, let me write here. So we'll say like it's something like sure, ax plus by plus cz equal to some constant d. Right? Kind of the three-dimensional analog of a two-dimensional line, right? Because your general equation for a line in two dimensions is ax plus by equal to some constant c. I know it's not the way we usually write it, but a line in two dimensions looks like ax plus by equal to c, which you could certainly turn into y equals mx plus b, but we don't need to. So that's your very general plane equation. And at least one of A, B, and C has to not be zero, right? You can't have zero equal to D. That's not the equation of a plane. That's just constants. And then a line, very generically, parametric equations, it's x of t equal to some x naught plus a multiple of t. What letter do I want to use here? I don't know. I wasn't really thinking about this. M1 times t, and then y of t is some y naught plus m2 times t, and z of t is some z naught plus m3 times t. Where essentially what we're saying here is this line contains the point x naught, y naught, z naught, and has direction vector. I guess I could have called it V1, V2, V3, but I didn't. V equal to M1, M2, M3. Those are the kind of general ways we think about writing the equation of a plane and the equation of a line. Is that kind of what you're asking about? Okay. I'm happy to say more. I'm just not 100% sure what we're going for. I dropped this the other day and it's like it kind of dented here and it's become a little less stable. So it's a little wobbly sometimes if I'm not too careful. I feel like there's something else here that I wanted to mention. Yeah, I know. So I remember the other thing. So last time I talked about how I didn't remember how to find the distance between parallel lines. And I didn't remember because it's super easy. So if you have two parallel lines, let me show you how you find the distance between them. And this kind of same thing goes for parallel planes as well. Kind of. So let's say we want to find the distance between the lines L1 given by the equations x equal to 3 plus 2t, y equal to 4 minus t, and z equal to, let's say, 3t. And line 2 is going to be x equal to 1 minus 4t, y equal to 5 plus 2t, and z equal to negative 6t plus 1. And the way we can see that these lines are parallel is that their direction vectors are multiples of each other. So we look at the first direction vector, your v1 is 2, negative 1, 3. And your v2 is hopefully a multiple of that, negative 4, 2, negative 6. And v2 is just negative 2 times v1. Okay, so here's all you have to do. Pick a point on one of the lines and then find the distance from that point to the other line, which we already know how to do. So whenever things are parallel, it's really just kind of, it always boils down to if you're trying to find distance between things, finding the distance between a line and a point or a plane and a point. Those are really the only things we actually know how to find the distance between. Everything else we just have to imagine as that problem after we've kind of distilled what we need to. So here on the first line, I would say that P equal to, let's just let T equal 0, 3 comma 4 comma 0 is a point. Let's call it S because I'm going to be smart about this. S equal to 3, 4, 0 is a point on the first line. And now all we're going to do is find the distance from L2 to that point S in the usual way. We're going to pick some other point on L2. And the thing is, the point we pick on L2, we don't know that it's the closest point, just like every time we've done this before. So we pick some other point on L2, which we'll also find by setting t equal to 0, because that seems easy. That point's going to be 1, 5, 1. Interesting that I chose to write z that way. Sorry. So this point is our p. It's 1, 5, 1, right? 1, 5, 1. Our s is 3, 4, 0. And now we're just trying to find the usual distance between a point and a line. And I'm going to pretend like I remember the equation. Line means sine, or line rhymes with sine. And sine means we use the dot product or the cross product. Cross product. So the equation should be, if I remembered it correctly, the distance is the vector PS crossed with the only other vector you've got, which is the vector that's pointing in the direction of the line. So our L2 vector is V2 divided by the, oh, do I remember what it is? Oof, I don't know. I really don't know, actually. I think you divide by the magnitude of V2. Good. Cool. I might remember it from now on. Maybe. We'll see. So then you would actually have to do the calculation, which is not the fun part. It might be the fun part. So PS crossed with V is going to look like the determinant of ijk. The vector PS is 3 minus 1, which is 2, 4 minus 5, which is -1, 0 minus 1, which is -1. And the vector V2 is -4, 2, -6. So that's going to end up equaling, okay, it's going to be I times the determinant of this 2 by 2, -1, -1, -2, -6, minus J times the determinant of the 2 by 2 where we cross out the middle column. So 2, -1, -4, 6, plus K times the determinant of 2, -1, -4, -2. And that ends up being, let's see, let's actually write it out. So we're going to get I times 6 minus 2 minus J times 12 minus 4 plus K times -4 minus 4. Be careful. It can be easy to accidentally think you get 0 when you get not 0. So our PS cross V is equal to 4I minus 8J minus 8K. And then we're going to want the magnitude of that. So the magnitude of PS cross V is going to be the square root of 4 squared plus -8 squared plus -8 squared, which is what, 144, I think. Is that really 144? Let's check it out. They actually pick nice numbers. I'm just surprised. You never just accidentally get a nice square number in there, but I think it is. We get 16 plus 64 plus 64. Yep, cool. How nice is that? Banner day. Okay, and then the magnitude of V2 is the square root of -4 squared plus 2 squared. Also, when you write this, you don't need to show, like, you don't need to write -4 squared plus 2 squared plus what, -6 squared. You should probably not write that as far as I'm concerned. You should write the square root of 16 plus 4 plus 36. Right? That's too much writing. So then you get the square root of 56. So it looks like our distance is going to equal 12 divided by the square root of 56. Neat. And then I will point out, but I don't think we need to do it. It's a similar process for parallel planes, right? If you had parallel planes, and how would you know they were parallel? Because the coefficients of x, y, and z would be multiples of each other. So for example, I'm not actually going to do the work, I promise, I think. For parallel planes, this first plane was like 2x plus 3y minus 4z equal to 11. And this other plane was, let's make it a different multiple, 6x plus 9y minus 12z equal to 2. Then you would just say, well, obviously they're parallel planes because the x, y, and z coefficients are all multiples of each other. The same multiple, I should point out. That's an important point. Then you just pick a point on this plane and find the distance from that point to that plane, which is the same sort of idea. You find the normal vector. So like here's your point S, you pick some other point P, you find the vector PS, you use your normal vector to your plane, and then your distance here is going to be, well, it's not a line, which doesn't rhyme with sine, which rhymes with sine, so it's got to be not sine but cosine, which means you use the dot product. So I know it's going to be PS dotted with the vector n, absolute value of that, divided by the magnitude of your normal vector. Cool. I'm just happy I remembered stuff. It feels very kind of circuitous to get there, like to say line rhymes with sine, and sine means the thing I can't remember the name of anymore. Cross product. But it works, right? I've said it enough times now that it's stuck inside my head. So if it works for you, great. If it doesn't, you'll figure something out. Okay, what else do we need? So that's kind of, in my opinion, the end of like the distances between things, angles between things, kind of content. So then I know the next kind of topic that seems like some people might be giving it a little bit of not very much attention is like the vector valued functions, and then talking about like velocity, acceleration, the tangent vector, the normal vector, right. I think not everyone's talking about them. So I don't want to do too much because it's not like it's kind of useful, but it's not that useful. So we'll try to say enough, but not too much. So vector valued functions, which we've already talked about when writing lines. In fact, let me just give you an example. So for the line that we have described with parametric equations like x equal to 3 plus 4t, y equal to 1 minus 6t, and z equal to 3t. Instead of writing that as three parametric equations, we can write it as the vector value function. And usually if it's a position function, right, because we're talking about kind of just where a particle on this line would be, we usually write it as r of t. And it's going to be just the x, y, and z coordinates as a vector. So it's 3 plus 4t, comma 1 minus 6t, comma 3t. And that's pretty standard, but if you prefer, you can all, some people like to break, specifically for lines, some people like to break apart the constant part and the direction part. So you could write this as 3 comma 1 comma 0 plus 4 comma negative 6 comma 3 times t. That would also be acceptable. But you don't only describe lines with vector valued functions. You can also describe all sorts of curves in space. So here's another example. And I will admit, I am not the best at this. Like this starts to require visualization of three-dimensional things, which can be challenging. I'll stop there. Yeah. So let's do some examples and we'll talk about kind of ways you can make this work for you. So let's look at this example. We want to find a vector function. Sometimes we leave off the word valued. A vector function for the intersection of these two surfaces, x squared plus y squared equal to 4 and z equal to x squared. So let's actually kind of think about what that looks like for a second. So x squared plus y squared equal to 4 is a circle in 2 dimensions, is a cylinder in 3 dimensions, because right, there's no z component, so there's no restriction on what z can be. So this is a cylinder of radius 2. Obviously, I can't draw all of it. And this z equal to x squared is a parabola in 2 dimensions, and it's a cylindrical parabola in 3 dimensions, meaning it's a parabola, right? It's this kind of deal. No, it's not a paraboloid. It's a cylindrical parabola, or it's a parabolic cylinder is the right way to say that. Meaning it's a parabola that's just getting extended in whatever direction we're missing. So it's z equals x squared, and then in the y direction, it's kind of like you have a, how do I say it the right way? It's like you have a line that's a parabola, and then you're like kind of like pulling down a shade that's a parabola shape. So you've extended this parabola that's just this linear, well, curvilinear thing into a surface that still has that parabola at any point. So it really is easily described as a piece of paper, right, in a parabolic shape. This is your parabolic cylinder surface, not to be confused with the paraboloid, which looks like the bottom of an egg, kind of, right, where you have circularness throughout it. This does not have circularness throughout it. I should say circular level curves, which we'll get to soon. So this other shape looks like, and I'm not great at drawing this one either. Sorry, you guys are limited by my drawing skills here. So there's my parabolic cylinder. And then we're basically trying to see where these two things intersect each other. So I'm going to draw over here. So like these points here kind of are going to hit right like there and there. And then it's going to kind of go up. So it's going to kind of do, and then you go, man, yeah, pictures here. Ooh, sure. And then it kind of goes around the back and does kind of the same thing. Oh, no. Kind of like that. Oh, it looks so bad. I would describe it as looking like a Pringle, which I know my picture does not do a good job of showing that, but it does kind of look like a Pringle because it's kind of going like up this way and kind of like down this way. Um, this is a great time to use graphing tools that are not drawing. So you can actually plot both of these things just to kind of see what they look like. We have your x squared plus y squared equal to 4, not 5, 4. So this bottom ball is right in the way here. And then we also have, let's make it look like some translucent surfaces so we can see things a little bit better. And then we also have z equal to x squared. So you can kind of see, oh yeah, it's up and then down and then up, right? You can kind of imagine it's a very kind of it's a much less flat Pringle than your usual Pringle. It's been stretched out this way kind of, but it has that kind of Pringle shape. So the question is, how do we describe that curve of intersection using a vector valued function? Well, let's see what we can do. And really kind of, yeah, it really kind of depends on what kind of stuff you're given. So here's what I'm noticing. This cylinder can be written, well, we can parameterize that cylinder. Or really any circle is super easy to parameterize. You let x or y be your radius times cosine and the other one be your radius times sine. So one way to deal with this part is to say x of t is equal to 2, I'm going to say cosine because that's pretty typical, 2 cosine of t, y of t equals 2 sine of t. And this works because literally if you plug this into that equation, your x squared plus y squared is equal to 2 cosine of t quantity squared plus 2 sine of t quantity squared, which is just 4 cosine squared t plus 4 sine squared t. And factoring out the 4, you get cosine squared plus sine squared, which is 1. So you get 4 times 1, which is 4. So this solves, or yeah, solves this equation, but now we're writing it parametrically. And then we're going to take our z equal to x squared, and we're going to replace x with what it's equal to. So we're going to rewrite this as z equal to, well, x is 2 cosine t, so it's 2 cosine t quantity squared, which is just 4 cosine squared t. So check this out. There is something cool is going to happen, I promise. Well, maybe cool, mathematically cool, I think. So we can now fully describe any position x, y, and z with a parameter t. We can say that our vector function r of t, which is x of t, y of t, z of t, is equal to, well, x is 2 cosine t, y is 2 sine t, and z is 4 cosine squared t. Now, I would say the problem with this is that it's hard to know you've done the right thing, right? Like it seems like we probably did the right thing, but like, did we actually? Well, you can use Desmos to help you see if you've done the right thing. Here's what I mean. So if you go back to Desmos over here, and you then, and I have to remember how to do this. I think you just type it as a vector. I'm going to type in the vector 2 cosine t, comma 2 sine t, comma, what else do I have here? 4 cosine squared t. And then, what's that? Thank you. Good job. Thanks. Say that one more time. Oh, thank you. Blowing it, really blowing it. Oh, you know what? I don't think I need the brackets though. I think I need them to be parentheses. That's the problem. Yeah. Well, one of the problems of, come back. Sorry. You remember how to do something that you kind of forget. And then you let t kind of go from, I think 0 to 2 pi. I should do it here. And then look, you can see exactly that green thing I've drawn is exactly describing the intersection there. It's kind of great, I think. It shows you, stop moving, please. And then you can turn those off for a second. Like, oh yeah, there it is. So I find this super helpful because I'm never confident that the thing I have done is actually the intersection. But if you can write just the parameterized vector, but right as the point, and you can see if it's actually the intersection of the surfaces you're looking at. Kind of cool, I think. I think it is definitely worth doing, at least in the beginning, to help you visualize what's going on. Questions so far? Kind of neat.
So the one being displayed is the one you have the
Right. So this thing being displayed is my r of t equal to the vector function 2 cosine t, comma 2 sine t, comma 4 cosine squared t. We're just writing it as a point. And then you have to make sure you let the bounds on t be big enough so you get whatever you're supposed to try to describe. All right. Let's see what else we've got here. Yeah. Yeah. So then you can talk about other things. Another kind of interesting one. So let me just show you one more. Similar nature, but a little different, is a helix. So instead of the intersection of x squared plus y squared equal to 4 with z equal to x squared, we now want to examine the helix, which we'll describe as r of t equal to the x and the y are still going to go around in the circle, but the z coordinate is just going to increase. So we're going to do this as, let's pick the same radius, 2 cosine t, 2 sine t, and then just t for z. And I really just wanted to show it to you. I don't have a lot to say about it yet. But if we look at this, we change this 4 cosine squared t to just t. There's part of the helix, but we've only got kind of one revolution. So if we let t go much longer, well, I went too big, sorry. There we go, okay. Don't get too crazy. And then zoom out a bit. You can see, oh yeah, it just kind of keeps going around and around and around and around and around. Kind of neat. We can say things about it in a little bit. But first, there's some other stuff we have to explore, which is, in my opinion, a little bit less exciting. So for each of these vector functions, we can talk about where the kind of particle traveling along the path might begin, what direction we're traveling, what the speed of the particle is, because it could be traveling up the singular constant speed, but it doesn't have to be depending on how your vector function is described. So let's look at, I feel like this one is not very interesting here. Sorry, my examples are all over the place here. Apologies. This is my only example. Sure. Okay. So let's look at the following vector function. R of t equal to cosine of t, comma sine of t, comma t squared. This is also going to have a helix shape, but well, we'll talk about it. So, sorry, let's see here. So I have to say words that I don't love saying. Sure. So what is the position of the particle at time equal to 0 and time equal to pi? Easy enough. We're just going to plug those values in. So r of 0 is cosine of 0, sine of 0, comma 0 squared. That's going to be the point on the curve 1 comma 0 comma 0. But then if we look at, say, r of pi, it's going to be cosine of pi, comma sine of pi, comma pi squared, which is going to be -1 comma 0 comma pi squared. So we're getting a lot of height while we go around the circle. What what is the velocity of the particle at time t? Well, good news. Velocity and position still work the way you think they should. Velocity is the derivative of position. Acceleration is the derivative of velocity. So our velocity at any time t is going to be just the derivative of r. And you're just going to take the derivative component-wise. So it's going to be the derivative of cosine, which is negative sine of t, the derivative of sine, which is positive cosine of t, and the derivative of t squared, which is 2t. I'll remind you, velocity is a vector, right? Velocity has a magnitude, right? A speed, but also a direction. If you just care about the speed, you have to find the magnitude of your vector. So I could ask, for example, what's the velocity at time 0? Well, it's going to be negative sine of 0, cosine of 0, 2 times 0. Not a very interesting result. And then the speed at t equal to 0 is going to be the magnitude of that velocity vector, which also happens to be 1 in this case, right? It's the square root of 0 squared plus 1 squared plus 0 squared, which is just 1. On the other hand, if I want to know what the velocity is when time is equal to pi, I get velocity of pi equal to negative sine of pi, which is still 0, cosine of pi, which is -1, and 2 times pi. And now the speed at this position is much larger, right? The magnitude of that velocity vector is equal to the square root of 0 squared plus -1 squared plus 2 pi squared, which is the square root of 4 pi squared plus 1. So a little bigger than 6. Much different than 1. So your velocity can really change depending on what's going on. More generally, we can find the speed as a vector, as a function of t as well, by just taking the magnitude of your velocity vector as the square root of negative sine of t squared plus cosine of t squared plus 2t squared. Sorry, that was a little ugly. which is going to be the square root of sine squared plus cosine squared, which is 1 plus 4t squared. And then you can see, oh yeah, if we plug in pi for t, we exactly get that there. So, yeah, we should go back. Sorry, there's so much we could say, and there's so much I don't want to kind of burden you with if you don't have to know it. Does that make sense? Like some of your teachers definitely will talk about this more in depth. Some of them will not. Let's go back to 2 dimensions for a minute and look at an easier example. So in 2 dimensions, we can still describe things with vector valued functions. So let's say we want to say our vector valued function is r of t equal to cosine of 2t, comma, sine of 2t, which you might recognize as being describing a path that's around a circle of radius 1, right? So this describes a path or curve is what I should really say. That is a circle of radius 1. How do you know it's 1? Because if you say, looked at the equation for the circle of radius 1, which is x squared plus y squared equal to 1, and plugged in cosine for x and sine for y, it would satisfy that equation. But that's not really what we're here to talk about. So there's a circle of radius 1. And we kind of want to answer a few questions here, like, what is the... All right, let me look here. Yeah. So what is r of 0? Where do we begin? Well, it's going to be cosine of 0, sine of 0, which is the point 1, 0. So right here is our beginning point. Which direction do we go around the circle? Well, what's kind of neat about circles is you can kind of make it work any way you want. You could pick a different way of organizing sine and cosine so that you went around clockwise or counterclockwise and you started at the top, the bottom, the left, or the right. It really just depends. A pretty typical way of doing it is starting at the right and then going around in the counterclockwise direction. So the way I really know to say this is just like, if we look at maybe the next interesting angle, which is pi over 4, we're going to get cosine of 2 times pi over 4 and sine of 2 times pi over 4, which is cosine of pi over 2 and sine of pi over 2. That's going to be 0, 1. So as the angle increases, right, as we go up this way, we're going to end up right there. Sorry, right there. So drawing the angle is not good. I apologize. That's kind of a mistake. What I really should be saying is this is our point here, and we've reached that point when the parameter, not the angle, when the parameter is pi over 4. Sorry about that. The angle is something totally different than the parameter. It just happens to make sense to be using typical angle values as values of t here because we're dealing with sine and cosine. So it looks like we are traveling in a counterclockwise direction because we started here and then a little bit later in time, we ended up over here. If we picked another time, like t equal to pi over 2, r of pi over 2 would be cosine of pi, comma sine of pi, which would give us the point -1, 0. So over here, we'd continue going that way. And over here at -1, 0, we're getting there when t is equal to pi over 2. So it seems reasonable that we're going counterclockwise. What's the speed of our particle that's moving around the circle? Well, this actually is kind of interesting, I think. To find the speed, we first have to find the velocity vector. So the speed, well, first we're going to find v of t as just the derivative of our position vector, which is going to be derivative of cosine of 2t is -2 sine of 2t. Derivative of sine of 2t is +2 cosine of 2t. And then if I take the magnitude of v of t, is going to be the square root of -2 sine of 2t squared plus 2 cosine of 2t squared, which is going to be 2. Because what we really have here is the square root of 4 sine squared of some angle plus 4 cosine squared of the same angle. You've got your typical sine squared plus cosine squared trig identity. So you have really 4 times 1 inside there, which is going to be the square root of 4, which is 2. So in this particular example, this particle moving around the circle has constant speed, which is kind of interesting. It's kind of noteworthy. And yeah, we have enough time. So we'll say 2 more things, then we'll call it. So what about the acceleration? Well, just like velocity is the derivative of position, acceleration is the derivative of velocity. It also has a direction to it. So the acceleration vector is going to be the derivative of our velocity vector or the second derivative of our position vector. And that's going to be, well, let's see, the derivative of velocity is going to be -4 cosine of 2t, comma, -4 sine of 2t. And here is something that is true in this instance. In this instance, velocity and acceleration are perpendicular to each other. Let's check. So if we look at, how do we check to see if these are perpendicular? We would check to see if they're dot product. Yes. So we're going to look at our V of t and our A of t. So we've got -2 sine of 2t, comma 2 cosine of 2t, dotted with -4 cosine of 2t, comma -4 sine of 2t. I think we're in luck here because we're going to get -2 times -4 is +8 sine of 2t, times cosine of 2t, plus 2 times -4 is -8 times cosine of 2t times sine of 2t. And those do add up to 0. And there is a truism here, which is that whenever your speed is constant, your velocity will always be perpendicular to your acceleration. Whoops, sorry. Which is kind of neat. And there's a pretty easy proof of it, which I don't feel like we should do right now. If you're in, I think it's Luli's class, it's in his notes somewhere. Right. So why would that be true? He says it wasn't going to prove it. Now maybe it will. So I said, there's a really easy proof of that. Do I remember what it is? Maybe. Well, let's see. So what did he said? I said that the velocity speed is constant. Yeah. How do we prove this thing? I think it's something to do with the fact that no, but we're not saying velocity is constant. We're saying speed is constant, which is a different thing, right? So, well, I'll have to leave you with a cliffhanger, and I'll think about it and remember and try to remember what it is because I know it's not that hard. It's basically you're basically saying when you're taking the derivative. Oh yeah. It's yes. Okay, so we want the velocity. Okay, the magnitude of the velocity is yes constant, right? So then if you square it, still constant, right? But the magnitude of the velocity squared is the velocity vector dotted with itself. Whenever you any vector, right? Any vector, if you dot it with itself, you're really just getting all the components multiplied together, which is the inside part of the square root, and then you square that to get the magnitude squared. So this is really v dot v equal to a constant. And then what you do is you take the derivative of both sides. So if you differentiate both sides, the derivative constant 0, and the derivative of a dot product still follows the product rule, which is that you're going to have the derivative of v times, I should say dotted with regular v plus regular v dotted with the derivative of v equal to 0. But those are the same. So you add them together and you say 2 times the velocity dotted with the derivative of the velocity, oh, that's acceleration, is equal to 0. Divide both sides by 2, and you get the velocity dotted with the acceleration has to equal 0, meaning they have to be perpendicular. Good. I would have felt bad. So let me walk through that again because I can see some slight confusion. So we're starting with the fact that we said the speed was constant. That's how we're starting with this. Because if something's constant, its square is also constant. But then we said, but the magnitude of a vector squared, I'll remind you that the magnitude of v is just the square root of its components. I guess there's 3 components. Squared, add it together. And then if you square both sides, you get the magnitude of v squared equal to v1 squared plus v2 squared plus v3 squared. But that's exactly just v dotted with itself. And then the rest of this follows up pretty nicely. V dot v is equal to c. The dot product kind of the product rule for the dot product does work. It is what you think it would be. So then you have the product rule here. You get your derivative times your not derivative plus your derivative times your not derivative. They're the same. Divide by 2. And you've got, oh yeah, the dot product of the vector and its derivative, which is the acceleration, has to equal 0. But that's only true if your speed is constant. If your speed is not constant, which is most of the time for these vector functions, you don't necessarily get that the acceleration is perpendicular to the velocity. You keep wanting to say speed, but it's not speed, it's velocity. All right, we will stop there because it's 4:01. We should stop. Make sure you got your name on the attendance sheet, and I'll see you all on Friday. And not that it affects us at all, but just a reminder, there's no class next Tuesday, right? It's Veterans Day, so don't come to school on Tuesday. I won't see you anyway, but just as a reminder.